Hello, everyone, and welcome to the second episode of the Wolfram Student Podcast. I'm Sam,
And I'm Rashank.
and we're your hosts.
This is the Wolfram Student Podcast, where every fortnight we dive into a new, innovative project done by high schoolers using the Wolfram language.
For our second episode, let's welcome Taein Kim, who'll be discussing his project on optimizing multilayered neural networks on Boolean functions. Hello, Taein.
Hello. Nice to meet you.
Nice to meet you as well. Can you tell us a little bit about yourself?
Yeah. So, my name is Taein Kim. I am now a senior in high school, so in 12th grade. I am currently attending Thomas Jefferson High School for Science and Technology in Virginia, and I was part of the Wolfram Summer Camp for high schoolers this past July 2022.
Great. And what prior experience with Wolfram do you have? Have you attended one of the camps or one of the other programs, or what's your involvement been like so far?
So far, it's just the Wolfram Summer Camp that I just mentioned. Before that, I had a little bit of experience because I had to, get familiar with the language, do some like the pre-camp tasks. But the camp this past summer, I think, is what taught me more about the Wolfram language. So all the syntax and like all the different ways to like use this language, I've learned from my camp mentors and lecturers.
How was camp this year? Do you want to share a little bit about that?
Yeah, so Wolfram Summer Camp was virtual, which is well, it was a new experience, and it was really different from like other camps I've attended because the one thing is it doesn't just focus on your project, right? So you'll actually be assigned to these like mentor groups and TA groups, and they're gonna assign you like adults that know the Wolfram language well as other people in like the same situation, which may be from like all parts of America or even like international. And all these people come together and like we discuss things we like about the Wolfram language. Like we'll play like games after work. We'll have project time. Sometimes a specific mentor will come out and lecture to the entire group. And all of these were really cool. And I think it was a really worthwhile 2 weeks. And it all culminated in a project that I've personally worked on, as everyone else did, and publishing it on the Wolfram website.
Great. And to kind of round up the intro, do you mind sharing your favorite Wolfram function?
Ooh, my favorite Wolfram function. Um, I was actually it's funny because I was actually asked the same question when I first started Wolfram Summer Camp, and back then I
Mhm.
didn't know that many Wolfram functions. But now I think my favorite function is the net chain method. is
Wow.
um is like a basic thing for machine learning where you make layers of a neural network and then you'll like put it all together using this method. And I actually use this method as like a core part of my project. I'll probably demonstrate that later.
Sounds nice. Well, now let's get into your project, optimizing multilayered neural networks on Boolean functions. So can you first give us like a quick summary of what it's about?
So when I first started this project, I knew I had an interest in machine learning. I've taken classes in machine learning in school, and I've had like some other summer programs, etc., that machine learning. And when I walked into the Wolfram Summer Camp, I wanted to do something along those lines, and I discussed these feelings to like Stephen Wolfram and my mentors, and they suggested that I make a machine learning model that could predict what are known as Boolean functions and their inputs and outputs. And Booleans are basically just like true false variables in computer science. And there are functions that take a set of Boolean functions specifically and then have like a fixed output. And I would make a neural network that would first train on a lot of Boolean data with a little bit of randomness mixed into it. And then there'll be like a separate test sets that the neural network could predict the output of. And I began with some simple Boolean functions, and then I like expanded it outwards, and I added more layers to my neural network to make it train better. And I think that was a process, but yeah.
Cool. Yeah, super interesting. I like how you took maybe what some people might call like a generic interest in machine learning, and because a lot of high schoolers, that's what uh, we have. At least for me, I remember that when I first got into machine learning, I was just interested in machine learning in general, and then you found a way to leverage the work from summer camp to make that very specific and narrow it down to this great project that we've got there. So maybe do you want to walk us through some of the key concepts or the key code blocks that kind of make this product go around, and maybe talk a bit about them?
Yeah. So I guess I'll go through my notebook then. First of all, to define what machine learning is, it's basically just getting a set of weights that are connected to each other, and then you would update these weights based on a given data, and then use these updated weights to predict other parts of the data, which is known like as the testing data, right? So when I began this project, after a short introduction, as I mentioned before, I'll have to create the data set. And because this set had to be on Boolean functions, I, as you can see over here, my first block shows the structure of the data set. And because I had 2 weeks, I decided to use 2 input to 1 output Boolean functions, which are essentially it takes 2 Booleans in, and then based on the type of the Boolean function, it'll give you 1 output that's also a Boolean. So first of all, as you can see in my inputs, the data has a set of vectors of size 3 pointing to vectors of size 1, right? And the vectors of size 3 are what are known as the input. So the first 2 numbers are the 2 Boolean functions, with 1 representing true and then 0 representing false. And then the last number signifies the actual Boolean function, which, as you can see, are coded up here. I just made this array for my own benefit. So 0 would be the AND function, 1 would be the OR function, 2 is NAND, 3 is NOR, and then 4 is XOR. So these 5 are probably the most commonly used Boolean functions in computer science. There are also many, many more. Like it goes up to 16 for 2 function inputs, and then it goes up exponentially for 3 and 4 function inputs. And it points to 1 output, which is also a Boolean function. 1 is true, 0 is false. And I would get every set of input for every given Boolean function, and I will put this in data, right? So there's 4 sets of input, true, 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 false, false, true, false, false, for each of the Boolean function. There are 5. So essentially we have 20 cases. But we know that 20 instances of a data is not necessarily enough to try and train a neural network. So this was a problem that I was like looking into, and I didn't want to manually create just more and more Boolean functions on more and more variables. So instead, what one of my mentors suggested to me in camp is first copy down this data multiple times, and then add randomness to it, like a little bit of a variable shift. So I'll probably mention that later, but it looks like the creation of the neural network comes first. So right here, I'm creating individual layers of a neural network, and one layer is basically just an array of weights, right? So the first 5 layers, notated by layer 1 through layer 5, are just simple linear layers, right? Set of weights, and then it'll take in a set of input and then take in a set of output. And because I'm going to, in my neural network, chain my layers in this order from layer 1 to layer 5, I need to make sure that the output dimension for one layer has to match with the input dimension for the following layer. So layer 1 has input 3 and then output 3. The input 3 is from like my dataset created before, because as we said, the input is a vector of size 3. And then output size 3. This just keeps repeating until the last layer, where layer 5 will take in an input of size 3 and spit out an input of size 2, and output of size 2. And what this output says is basically just the class, right? It's either going to be 0 or 1 based on the probability in which this specific instance has an output of 0, which is false, or 1, which is true. And then a softmax layer, and I had to do some research on what a softmax layer is before I started putting it at the end of my neural network. But it's basically a layer that converts its input values into a set of probabilities for each class. So um, it'll take in a set of input, and then the output will be based on, let's say, one number for each specific class, and then the class with the highest probability will be um, decided on by the neural network. All right. So afterward comes my pre-processing, and as I said before, I had to copy down my data and then add robustness to my model. So first of all, what I did was I flattened my data into a table 100 times, and then now we have an array that has 100 copies of my data. So now we have 2,000 instances. So that will probably be enough for training our data set. But if we just use this as is, then probability wise, every instance of our test data set will also be exactly in our training data set. And we don't want that because a neural network actually has to predict information that it doesn't know. So what I did was for every input value, so the first two values of the size 3 input vector, I added a random real between negative 0.1 and 0.1. So then every instance of the data is unique and I can train on it well. And this was a way that, again, Stephen Wolfram suggested to me, and I, got to implementing it. I was surprised because this actually made my data training process more rigorous. And then lastly, I did a train val test split. And essentially, a train val test split is what you do for every machine learning data, right? So you have a given data, and you want to split it into a training set, a validation set, and a testing set for your model. A training set is what your model learns on. So in this case, it's what's known as a supervised learning, where your model will know both its inputs and output values for every specific instance of the data. And then validation is done along with training. Then lastly, the testing set is to actually find out your accuracy after your model is completely trained on your training and validation set. And then you get your accuracy and your precision measurements based on that. So because I couldn't directly split into 3 datasets, because the standard ratio for train val test is 80-10-10, right? You also see many others. So first of all, I split the data into a training set and then another set. So train test it defaults to an 80-20 split. So the 80 part is going to be my training data. And then the next up is val test, which is going to be the remaining 20% of my data split into half. So then one half is going to be the validation set, which is 10% of the entire thing. The other half is going to be the testing set, which is also 10%. So afterward, all we've got left is first chaining the layers, right? And as I mentioned before, the net chain method right here is my favorite function. And we have all the layers that I've explained before chained together with the tanh or the inverse tangent activation function in between. And the activation function is basically a function that's used in between each layer of a neural network that is just applied and spits out a value between a certain bound to prevent it from going up way too far, or going down way too far, or doing other wonky things with the data. So we're basically just bounding it. And with an activation function, the neural network will run much better. And then after that, we use the net train method. And one thing I like about the Wolfram language is that it's very straightforward, right? So there's a net chain method that lets you chain all of your neural network layers together. And there's a net train method that you can just call immediately with your training and validation sets, and it'll just do it for you, right? And training actually didn't take that long. Usually, the bigger your data, the longer your training takes. But I just had to wait for a couple of minutes, and during training, you could see my accuracy going up and my loss going down, which is standard for any neural network. And the last thing I did was getting and visualizing the results. And this is another thing that I've asked for a lot in terms of like other people's input, because there are a lot of ways you could visualize results in a neural network. But the things that I've stuck to are first what is known as a confusion matrix. And it basically visualizes every instance's actual class versus what the model predicted it as. And as you can see, here's my confusion matrix. And most of the instances of the data, of the training data, are on the main diagonal, which means it's trained correctly. And we also have some misclassifications, but it's kind of difficult to have a completely perfect neural network. So overall, with an accuracy of 92.8%, almost 93, I'd say our network at the end was pretty reliable. And next one is what's called a ROC curve, right? And it lets you visualize the false positive rate, which is basically when the neural network predicts a certain class, but it ends up being something else, versus the recall, which is like your actual accuracy. So the ideal ROC curve will be almost like what I have right now. Is it goes straight up and it goes straight across. And the larger the area under this curve, the better your model is. And lastly is a density plot. And this visualizes the boundaries for which my model actually makes the decision. So it's not necessarily a measure of accuracy, but it's rather a visualization of the two variables. So as you can see, one axis is the first input for my Boolean function, and the other axis is the other output. And there's an almost linear boundary going across, which means that if a certain instance is on one side of this line, then it's going to be classified as either true or false. And then if it's on the other side of the line, it's going to be classified as the other one. I think that's almost all I had for my project. Yeah.
So did you test out your final neural network on any new data once you had it?
Mostly of
Like,
my data was self-created. So I actually set aside some of my data as a training testing set and got rid of the classes to see how it does.
and what did you find from that?
Well, essentially what I found from that was because I added robustness to my model, there was going to be some inaccuracies. But for the most part, a neural network is able to predict the outputs of a Boolean function set. And what I was thinking of doing, if I had more time for this project, was actually to add more variables to this data set, because as you can see, my data set right now is a little bit limited, but it still makes sense in a way. But if we add more variables, we can maybe see the boundary for this graph kind of like expand. Maybe we'll see more non-linear boundaries and stuff like that.
Sounds cool. Um, what was your favorite part of the project?
Oh, my favorite part of the project. There was actually a lot of favorite parts of my project. The first part was one thing that comes to mind is like all the help and support I got from other people during the camp, because although I knew how like neural networks worked pretty well, I didn't necessarily know how to implement it in the Wolfram language when I first began camp. But I had a really helpful mentor, and I also had classmates that did, or campmates, I guess, that did things on like a pretty similar topic. So from them, I could get inputs. I discovered new Wolfram functions that I haven't ever seen in like other coding languages, and kind of just trying them out and seeing them work, I think was really exciting.
Yeah, for sure, for sure. And what was the most difficult part to code, out of curiosity? I mean, this entire project is, of course, incredibly complicated. And I know from my experience at the camp, then that once you start diving into a topic, it can take so much time just trying to get your head wrapped around everything. But for you, what was the most sort of challenging part?
Well, a pretty big challenge was obviously the time pressure because although Wolfram Camp was a very good experience, it was also very short, right? In 2 weeks, getting the entire project done and then like, writing a paper out of it. So some parts that I've specifically struggled with was first creating like each layer because um the ultimate goal of like one of the big goals of my project is to get an accuracy measurement on a testing set, right? Just absolutely just visualize how my model did. And when I first tried to do that, um, I ended up finding out that without a softmax layer, I couldn't do that, right? Because that's just how the Wolfram language is. And so I had to look through the documentation of a lot of neural network layers to find out like why I can get this accuracy measurement. And later on, I figured out that because I didn't have like probabilities for classes that the neural network could actually make decisions on, it couldn't get an accuracy measurement. So I shuffled around some more. I looked at projects of like previous camp people, and some of them use neural networks with this softmax area with two classes. So I tried implementing it, and it worked. And another difficult part of my project was actually chaining the networks and training the data. And obviously, it isn't complicated code right now as you look at it, but pretty funny mistake I've made was I made all the layers and then forgot the activation functions. So I was wondering why my neural network was performing so badly because like the loss had barely decreased at all and the accuracy was pretty bad. And then I realized that activation functions aren't necessarily built-in neural network layers because when I created like linear layers, obviously there weren't activation functions inside of it. So then I looked into it and then I realized that you can literally just directly put in activation functions into NetChain. So I did it in between every layer except between layer 5 and softmax. And then after that training, the results just came afterwards. And I had to do a lot of modifying on my net chain to actually get my net train to work. And some other parts, maybe just you know getting dimensions to work, right? Sometimes your array would go out of bounds. Sometimes I'd like flatten a table wrong, and then like the net chain method wouldn't take it in because there was a dimension mismatch. Just little errors like that were pretty difficult to solve. But at the end, I got through, and I had a complete project. So I think that made me more happy because of all the things that I had to do in between.
Yeah, the errors with the Wolfram language when you're doing a project on a time crunch can definitely be frustrating from
I agree.
camp. How did you decide on using tanh as an activation function in your neural network?
Well,
Was
the first thing was 10H I was the most familiar with because I also do a lot of math studying, and 10H was a very straightforward function, right? It goes between -1 and 1. It's like the ideal bound you can think of. And I also know of other activation functions such as ReLU or other, some other sigmoid or some other stuff. But at the end, I think it was just like familiarity. And I actually experimented with like ReLU and sigmoid as well. And it ended up being that 10H did the best and I was the most familiar with it. So I just ended up choosing it.
Thanks for giving us more info about your project. I
Yeah.
think that's some work, and I'm excited to see how you take it forward. And talking about forward in the future, just wanted to ask you what your thoughts are about the Wolfram language, how it compares to other languages such as Python, for example, or Java or C++ if you've used those, and how you might use it going forward.
Yeah. So when I learned about the Wolfram language, and I'm acquainted with other programming languages as well, more specifically Java and Python. And I've done like machine learning projects, I've done like algorithm building on all of these. And one thing I think that makes the Wolfram language unique is just how easy it is to do like simple tasks, right? And I specifically remember like a kind of a funny task that was assigned to us while we learned about the Wolfram languages in the first few days of camp. And they told us to use the Wolfram language to find the location of the first, like the closest 10 airports to Rome. And that's not exactly a task that's assigned to programmers when you're coding in Java and Python. And I was like, how am I going to do this, right? Am I going to pull up like an image of a map? Am I going to be given like data to work with? Then it turns out there was just like a search function that got me the exact data that I was looking for. It would just spit it out, right? It was one line, that was it, versus other programming language, which would not be able to do that. And like another thing was maybe like image processing, right? In addition to like pulling up images instantly, it would also be able to like detect colors, like detect what it is with just a couple of lines. And all of this was like really convenient compared to other coding languages. And I think that's what I was impressed by. And when you're doing computer science and machine learning projects, we all know that it involves a lot of coding, right? All of your code will go up to like hundreds and hundreds of lines sometimes. But in the Wolfram language, it doesn't necessarily have to be that way. And after you're done, it's easier to compile, it's easier to like look into, and then it runs faster. I think is a good thing about the Wolfram language.
Yeah, and I particularly like your point about the documentation because all the documentation for Wolfram is, done in-house by the team and by the employees who obviously know a lot about the language as compared to, hunting around online for open source documentation, which obviously is an entirely different, and I wouldn't say better or worse experience, just, a different style of working with some people might like. And uh, though I think for beginners, obviously, the Wolfram language could be easier to, kind of gain a foothold in, which is what I did with my machine learning work. So yeah, thanks for coming here and talking about your project. Is there something you would like to add? Is maybe a last note?
Well, my last note probably. I know I had a very specific field of project, which is machine learning, and because the
Mhm.
Wolfram camp was short, there was a lot to improve, and I kind of look forward after that to using like these all these machine learning functions to do more complicated tasks, like for example image processing, because I have a little bit of experience in that area as well, and applying machine learning to these images. And I think it would also be like much easier to do it in the Wolfram language. So yeah, it makes me excited for the future of Wolfram, and overall I had a really good time in during camp, just creating my project and otherwise.
Yeah, sounds good. Uh, well, your project was really interesting, and thank you for sharing it with everyone. And we're looking forward to see what you finish in the future.
Of course, thank you.
Yeah, excited for whatever you do and keep us updated. And I'm sure as you post more things to the Wolfram community, our readers would also like to see the work you're doing and maybe learn from your code and maybe implement some of that in their own projects and take inspiration. So thanks so much for joining us once again, and glad to have you. Thanks for listening to this episode of the Wolfram Student Podcast. We hope you learned something new and took away insights from today's discussion. If you want to be featured in a future episode, fill out the form at tinyurl.com/WASP-interest-forum.
And finally, be sure to join us in 2 weeks' time when we discuss with Nika Chishoy about her project on implementing many-valued logic in the Wolfram language. Once again, thanks for listening to the Wolfram Student Podcast.